Hello, everyone. Welcome to today's AFMS seminar series. It's my great pleasure to introduce today's speaker, Dr. Krishna Talluru. Dr. Talluru is a lecturer at the School of Engineering and Technology, UNSW Canberra, and he's a member of the Hypersonics group. He completed his PhD at the University of Melbourne, and he subsequently took up research positions at the University of Newcastle and University of Sydney, working in a wide range of turbulent flow phenomena, including rough wall flows, wakes, jets, atmospheric and buoyancy-driven flow, to name a few. Currently, he's working on compressible wake flows and is a key contributor to the high-speed working group hosted by NASA. And today, he's going to talk about flow oscillations in a high-speed wake. Thank you, Krishna. Mike, is over to you.
Are you able to see my screen?
Yeah, I can see.
Okay.
Yes.
Yeah. Thanks, Aman. Thanks for the introduction and the invitation to give this seminar. Before I start, I wanted to just kind of briefly introduce myself once again. I did my bachelor's in IIT Delhi and then worked as a school teacher for 2 years before I moved to Melbourne, doing my PhD with Professor Ivan Marusic and Professor Nicholas Hutchins. And then I did several research positions at Newcastle and Sydney before I moved to Canberra 3 years ago. And I got my lecturer position 2 years ago here. And I'm a member of the Hypersonics group headed by Professor Andrew Neely. And I want to also acknowledge Associate Professor Sudhi Gai, whom I'm working very closely here. And my student, Akshay Kumar, he's in his first year, PhD student here. So I thought, the better way to introduce my topic is to use a statement such as, what goes up must come down, and then try to link up why it is important and how it is an engineering problem as well. So we can also say this as what goes up must come down or burn up. And I'll give you some statistics to justify what this title means. So if I read this, as of 2022 January, there are about 7,800 satellites up in the space, of which only 5,100 are still functioning. So those which are not functioning, eventually they will fall back as space debris. And and it is essential that we know where exactly they will fall, and that's why I framed this topic or the title of my seminar as what goes up. Now, whatever we're putting up into space will eventually come down, and it is our responsibility to understand where the objects that come down are properly displaced or deposited. So I've broken up my seminar into several episodes, following the trend these days of, on the Netflix series and so on. So my episode 1 is the problem. I'm going to describe what the problem is, and then we will develop in later episodes what are the fundamental issues and then some possible solutions. So as I said, the prediction of where and when the final impact happens is very, very difficult, because as these objects re-entry the atmosphere, they are also simultaneously burning, which means their shape is changing, as well as they're experiencing different atmospheric conditions, the density, the pressure, and the temperature. So everything needs to be calculated in real time to kind of predict what the trajectory is going to be. And in my opinion, that the wake, which is the flow behind these re-entry vehicles or a supersonic aircraft, plays a key role in determining the trajectory. The reason is if the wake is oscillating, and it is going to cause significant variations in the drag force, which will eventually affect the stability or the maneuverability of the vehicle. And that is key to predict where it will eventually die down. So the key research question here is understanding those origins of oscillations in a high-speed wake and try to control them or use them in a more efficient way or an effective way to stabilize the vehicle. So let's go back a step and understand what is a wake. I know most of you would know this, but I thought I will gradually develop, and for those who are not so familiar with what a wake is and what are some of the fundamental physics associated with it, I thought I will briefly touch upon that. So let's look at a simple uniform incompressible flow. So we are looking here for an incompressible wake. And if I put a bluff body shown such as this, can be a sphere or a cylinder, a circular cylinder, what you see is the flow stagnates on the center line or the symmetric axis of the body. And then you have this bound layer developing on either upper and lower surfaces of the object. And if you look in more carefully, what the boundary layer experiences, initially it goes under a favorable pressure gradient, and then a certain location or certain region of the cylinder, it will experience zero pressure gradient, and then eventually adverse pressure gradient, which will force the flow to separate off the surface. And at that point of separation, the cumulative vorticity that is present in the boundary layer is released as a vortex. And we often call this as vortex shedding. And this has been studied quite extensively. This doesn't need an introduction. And the famous work by Roscoe, Bierman, Berger, and Williamson, there's several works that have confirmed that you can characterize these shedding frequency, often used often use a Struhol number to kind of characterize this frequency or non-dimensionalize it. And what you use is the shedding frequency F, and you need a length scale and a velocity scale. So what they found is for a wide range of bluff body shapes, if you use the length scale as the wake width and the velocity scale as the free stream velocity, you tend to find a universal Struhol number for a Reynolds number greater than 300. So that is very well studied. Now, the topic of today's presentation or seminar is on compressible wake, and let's see if such a universality still exists for compressible wakes. So again, a compressible wake is slightly different. We will see, I'll go through the same process of how a compressible wake looks like. So here, I'm also considering a uniform flow, but it's a supersonic or a hypersonic flow where the Mach number, which is another non-dimensional number that represents the ratio of air speed related to the speed of sound in that fluid medium. So once you have a high-speed flow or a supersonic or hypersonic flow, you experience a bow shock, and the flow experiences a bow shock, and it is again stagnated on the axis of the bluff body. You also have a bound layer developing. In addition to what we saw in an incompressible wake, in a compressible flow, you have a bow shock, and it is followed by an expansion fan, which helps the flow to remain attached for a longer length on the cylinder surface. And at that, eventually at some point downstream or along the body, the flow will separate, and you have a lip shock and a shear layer developing. And these two shear layers on the upper and lower surface, they converge to a narrow region, which I call or traditionally called as neck region. Downstream of that, you have a recompression shock because the flow has to be turned back to being parallel to the free stream. And with this, you have a very stable or a steady or quasi-steady recirculating regions being set up within the base, the cylinder surface, the two dividing streamlines, and the neck region. So this is quite different to what we saw in an incompressible wake. In an incompressible wake, you do not have a confined region that holds these recirculating regions. And this has actually led to many researchers think that this problem can be treated as quasi-steady, which means I just have to solve a steady state problem of a compressible wave. And they didn't give or pay enough attention to the dynamics of the oscillations that were only recently observed. So I'm going to show an Euler simulation that was reported by Schmidt and Shepard from the Caltech group back in 2015. So this is just an inviscid simulation. There is no viscosity. And yet what we observe is that the point of separation is oscillating. It's not a fixed point. And you also see a quite drastic or dynamic oscillations in the neck region. And this is just an Euler simulation. We can also, they also provided evidence from experiments. So this is a shadow graph video of the near wake region at Mach 4 of a cylinder wake. And they then looked at the image intensity. They computed the Fourier spectrum, and they found a dominant frequency of about 16 kilohertz at these flow conditions. And they then varied the Reynolds number and Mach number to see if there was any universal scaling. So that brings me to the second episode. Do we have a universal scaling for compressible waves? So I think the starting point they took was just using the traditional definitions of Strohol number and Reynolds number, which is primarily based on the cylinder diameter d and the free stream velocity. And with these, we were able to pretty much see some sort of universality in incompressible wakes. But in the case of compressible wakes, you see that there is no clear scaling, and there's a large experimental scatter too. So they also compared with the incompressible wake flows that Roshko has done previously. So clearly this demonstrates that there is no scaling with these chosen definitions of Strohol number and Reynolds number. Then this brings us a question, are there other important length scales? So let's consider. So here is just a static image. So if you look at a possible length scales that we could use, we already used cylinder diameter. We could use the distance from the base or the rear end of the cylinder to the neck region. We could also use the width of the neck region as well as the shear layer length from the point of separation to the point of the neck. So what they found, they in their paper, they actually used the neck width and the slip line length as the reference length scales, and they use the free stream velocity or the pre-shock condition. And they kind of say that they found some sort of scaling. But my question, looking at their results as shown here, there's a very large scatter. It is changing from all the way from 0.35 to 0.6 within their uncertainty levels. So that actually kind of raised a question, is this the right velocity scale and length scale to be used? And following this study, fast forwarding to 2022, there were two studies, one by the IISc group in India, and they kind of followed the same methodology of Schmidt and Shepard, and they said they find similar results. And more locally, the study by Avasti et al. At UNSW Kensington campus with the Condulan's group, they have done similar experiments, and they also kind of suggest that there's a broad agreement with the universal Strohol number proposed by Schmidt and Shepard. So here we raise a question, about using the pre-shock conditions or the free stream parameters as was proposed by Schmidt and Shepard. We will examine and possibly look at an alternative scaling that we could use, which is more physically meaningful, also leads to better scaling That brings me to episode 3. I call this Gold Legacy. I am a firm believer that a lot of the good work has been done in the past, in the 50 years or so, and I do want to give them due credit. So here I'm going to take 2 statements from the book by Hayes and Probstein. I'm going to read it out verbatim because it's quite a profound statement. So he says in the book that for the most part, boundary layer theory in hypersonic flow is no different from boundary layer theory at lower speeds. On blunt bodies in particular, local flow velocities are subsonic or moderately supersonic or much of the inverse. So if I try to infer this statement properly and give my own interpretation, what I understood or what I can say is that the boundary layer developing downstream of the bow shock is actually governed by the post-shock conditions. And so therefore, anything that happens within the boundary layer, such as the flow separation, is also going to be governed by the post-shock conditions rather than the pre-shock conditions. So that is one key inference I make, which will actually tell us we could possibly use a different velocity scale. So we'll come and revisit this statement again. So the second statement is also equally important. The hypersonic limiting process, that is when the free stream Mach number becomes very large, the flow pattern, the pressure coefficients on a blunt body are found to be independent of Mach number. This is also otherwise called as the Mach number independence principle, quite well accepted in the community of hypersonic flows. So the second statement leads to this insight, which one can actually analytically derive this expression for the Mach number just downstream of the bow shock, shown by ME. And what we can see is that it is purely a function of the fluid. The gamma is the fluid property, and it is purely a function of the ratio of the base pressure, which is the pressure within the recirculating region, compared to the stagnation pressure just upstream of the bluff body, but downstream of the shock. And we can then look at some of the experiments or the numerical simulations that were carried out at UNSW Canberra about a decade ago. What they found is, in fact, that ratio becomes constant for Mach number above 3, which clearly justifies the Mach number independence principle. In other words, if you carefully look at the vertical axis and the horizontal axis of this plot, it is the ratio of those 2 base pressures. If I go back, and they are both downstream of the bow shock. And secondly, they used a Reynolds number they call RE2D, which is a Reynolds number based on the post-shock conditions. Okay, the suffix 2D refers to the post-shock conditions, and 1D refers to the pre-shock conditions. So together, these statements have actually helped me to think, there must be an alternative scaling. If you look at the physics of the boundary layer developing downstream of the shock, it seems more sensible to use the post-shock conditions rather than the pre-shock or the free stream conditions. So we will see, if we can provide further justification or analytical reasons to justify this. So again, going back to about 70 years ago, so Shaw was one of the first person who related the wake unsteadiness to acoustic perturbations within the recirculating region. So here, if I look at this expression, the N is the wake oscillations, and the other important ones are U infinity is the free stream velocity, and UW is the wave speed of those perturbations within the recirculating region. And Lighthill, this is as a chapter in the book by Rosenhead, he expanded or extended this analytical reason and included the Mach number. So this is a bit tricky, but let's pay a minute and pay attention to this. So what he proposed is this Mach number times lambda. He wrote it as omega L by A. And if you rearrange this, what you find is lambda is omega L by U, and this is nothing but it is equivalent to the Struhol number in the current literature. But what we can see is if I replace lambda by Struhol number and omega L by A, which is the acoustic Struhol number, the Lighthill's criteria says that the acoustic analogy works when the ratio of these two is equal to 1. Okay, so this is an analytical result, and we will see, we will apply this result against the experimental data and see whether they actually agree or satisfy this criteria. And we will see which velocity and length scales actually satisfy this. So here we are going to, because we want to compute RE2D as for the reasons I explained earlier, I'm just going to estimate based on the pre-shock conditions, but by multiplying by the corresponding viscosities, because the temperature changes, the viscosity changes post-shock. And we can also derive the Struhol number ST2 based on the upstream Struhol number definition. And for the existing data that I found in the literature, Schmidt, Shepard, Avasti, and Tasu, as well as our own results a decade ago, we are able to find all these quantities by using some of the normal shock conditions. The normal shock conditions are, justified in the sense because the boundary layer is going to be developing from the stagnation point, and the conditions around that stagnation point can be estimated using the normal shock relationships, because the shock, the bow shock only starts to curve only at some angle relative to the center line of the cylinder. So what we see here is for most experimental cases, the Struhol number, the acoustic Struhol number divided by the m times lambda, or m2 times Struhol number 2, it is pretty close to 1. And I also plotted them in a graphical way here. So the y-axis is the ratio of acoustic Struhol number divided by the Mach number times Struhol number, and the x-axis is the post-shock Reynolds number. We see pretty much most of the experimental data, they agree on they are very close to 1, except for the Schmidt and Shepard case, as well as the Avasti 2022 case. I think we believe that there is a lot of uncertainty in the experimental data that Schmidt and Shepard reported, and we also think the Avasti et al. The flow or the wake is more transitional, and so there might be some deviations from the Lighthill's criteria. So what we also notice is this product M2 times ST2 is also independent of RE2D, kind of establishes, this establishes both the Mach number and Reynolds number independence. So once you have sufficiently high Mach number, you can also use this to kind of predict what the Struhol number would be in post-shock conditions. We then proceeded because in the case of Schmidt and Shepard, they used the dividing streamline as the appropriate length scale. So we haven't yet finalized about what is the correct length scale. So far we proved that it should be the post-shock velocity scale that should be used for the Struhol number definition. But there is still a doubt, whether it is the cylinder diameter or should we use the dividing streamline as the appropriate length scale. So what we find is, yes, in fact, they also see a very decent agreement, a very good agreement, even if you define screw hole number based on the dividing streamline. But we believe that it's more complicated to estimate the dividing streamline from either experiments or from your simulation data, because it's highly dynamic. So there is no, although you have a fixed, or even sometimes the separation point is oscillating, you cannot very well define the neck region. And so it becomes very difficult. The uncertainty is much, much larger in finding the dividing streamline. So we are of the opinion that we can still use the cylinder diameter, and you can still get a very good agreement for the revised screw hole number definition. So far I kind of explained, I raised a question about the universality. I pointed out some of the existing flaws in the literature and kind of posted or postulated a new scaling that may give better agreement or better universality in the screw hole number for compressible wakes. Still, we haven't answered the question that I raised, the key research question: what is the origin of these oscillations? What is the cause for these oscillations in the neck region? So there have been predominantly three theories. One theory says that this oscillating point, the separation point is oscillating, and those oscillations are just being advected downstream, and that's what you're feeling or observing in the neck region. So that's one of the theory. And the second theory is, they say that there is an other mechanism, because there is a reverse flow, and this behaves like a reverse jet, and there are additional mechanisms or additional perturbations happening in the neck region when the two shear layers convolute. And that is what is causing or setting up these acoustic or kind of dynamic loop within this confined region. And they call this as acoustic resonator analogy. And the third possibility is, although I have represented here the dividing streamline or the shear layer as a very thin line, in fact, what we see is the shear layer is actually quite a fluctuating bit. And if you look at across the shear layer, the velocity within the recirculating region is predominantly subsonic or mildly supersonic. And within the free stream, we know it is still supersonic. So there is a strong velocity gradient across this shear layer. And we believe that velocity gradients kind of introduce this Kelvin-Helmholtz kind of instabilities. And those instabilities are just being advected down into the neck region. So these are all possible theories. And we are currently still in the process of finding answers to these three theories and kind of conclusively answer. So we are going to look at some of the key parameters we think affect the wake oscillations. So we think the free stream turbulence within your tunnel or in your simulations could be affecting your wake oscillations. There's a common theme called a receptivity problem in hypersonic flows. How the disturbances are processed by these shocks, and how do they affect the flow development downstream. There is also the Reynolds number effect, whether the wake is laminar or the boundary layer is laminar at the point of separation, or is it turbulent at the time it separates. And we also think there is the geometry of the object. In this case, this is curved. You can have a floating separation point. But what if you have objects, blunt bodies with sharp corners? where you're forcing the flow to separate at those points, would you still see these oscillations? So these are some of the parameters we think are important. And we're going to take an experimental and a numerical approach to kind of answer these, the dependency of these parameters and how they affect the wake oscillations. So our plan is we have experimental facilities here in Canberra. The middle one is a supersonic wind tunnel. It can go up to Mach 3.4, between Mach 2 and Mach 3.4. We also have a shock tube we call T-ADFA, and it can do hypersonic flows between Mach 6 and Mach 10. And my colleague, Woutin, he's currently at TU Delft. They have access to supersonic wind tunnels that can go up to Mach 4.5 without condensing. And I'm also collaborating with Professor Richard Sandberg at Melbourne Uni with his hipster code. And he has previously done some simulations and looked at a wake problem between laminar and turbulent wakes about 10 years ago during his time at Southampton. With this combination, we believe we can completely span a wide range of Reynolds numbers and Mach numbers, and both experiments and simulations, to kind of conclusively answer the questions that I raised before. For this, we want to primarily stick to very simple canonical geometries as shown here. It's a 2D cylinder, the left one. This has a two-dimensional shock, and it induces kind of a floating separation point that can be altered. If I use what I call a D shape, it'll still have a two-dimensional shock, but it'll have a fixed separation point. In addition, I can tilt or rotate this object related to the flow direction to kind of study the effect of fixed and variable angle of attacks and how do these induce wake oscillations. And finally, we want to also test a conical shock, a cone, where you would have a three-dimensional shock. We know that a 2D and a 3D shock are quite different, the way they process turbulence intensities or free stream turbulence. So we want to see how 2D versus 3D shocks affect the wake oscillations behind these bluff bodies. So we have done some simulations. My student Akshay has done some preliminary simulations using a code US3D that we have access from University of Minnesota. Professor Graham Candler, he has kindly shared with us that code. I'm just going to just show a very quick snapshot and what we have found so far. I would say this is still under development, but so far what we found is that for the Mach 4 and free stream Reynolds number of 2.7 times 10 to the power 6, we observed that the separation points, they both oscillate around 6.4 kilohertz, and they are out of phase, just as what we observe in an incompressible wake as well. And at the neck region, which is shown by the spectra plot in B, we observe that there is the dominant, the second harmonic or the first harmonic of 6.36. So the frequency doubling happens because the disturbances from these two separation points kind of contribute to doubling the frequency. And it also kind of supports the acoustic resonator analogy that we discussed based on Lighthill's criteria. And lastly, we also looked at just downstream of the neck, and we found some quite an interesting behavior. We see that as a broadband high frequency peak is kind of developing very, in a very short distance from the neck. And we kind of hypothesize that if you look at carefully how the recompression shock is formed, there are several weak compression waves that are present in this region. And we believe that all those weak compression waves are contributing to form this broadband high frequency peak in the velocity spectrum. I mean, this is still, as I said, this is still under development. We want to do a bit more deep dive into the simulation data to provide much more stronger evidence for this. So the end vision, I mean, so far I've been telling several aspects of compressible wakes and what our approach has been. But our end vision is kind of to study, when we have a much more complex geometry and you throw this in space. I guess most of you know about this Pac-Man, which is a video game character. So such a geometry like this, and it is changing with in time. How do we kind of understand the wake behind such an object? So eventually we want to see, we would like to be able to predict what these oscillations are in real time and be able to actuate or introduce some active control to stabilize the vehicle. So we will be using a bit more complex geometries, such as the one on the left side, call this Pac-Man geometry. The good thing about this is you can have a fixed suppression point on the top side or the upper side, and you can have a floating suppression point on the bottom. So you are actually forcing the flow to behave asymmetrically. So far, with the canonical geometries, there is sense of symmetry about the symmetric axis or the cylinder axis. But with this, you can introduce that, as well as you can rotate this object, and you can create the Pac-Man and different angles of attack. We also want to try out, once we understand the origins of these oscillations, we want to try both passive as well as active control schemes and try to mitigate or reduce at least the strength of these oscillations. I want to, kind of acknowledge all the collaborators. I'm really grateful to them for being part of this project and, agreeing to, I mean, they first of all agreed to, be part of this project, and they're contributing their time and resources. So with that, I also wanted to take this opportunity to advertise the Australasian Fluid Mechanics Conference. This time we are hosting it, UNSW Canberra, for the first time in Canberra. So the website is up, and you can use this QR code to kind of reach out, and we hope you all will attend the seminar and make it a successful one. And I will thank you, and I'll just leave this slide just running. I will take any questions if you have.
Thank you, Krishna, for this insightful presentation. So I now invite the audience, if you have questions or comments, please feel free to unmute yourself and speak directly, or you can also type your questions in the chat box.
May I ask a question?
Yes, please.
So regarding the scale, when you consider the downstream condition as an appropriate scale, I think that's intuitively reasonable, because the reason that we have a shock wave is that the upstream flow cannot communicate with downstream flow. So basically, everything is disconnected. And
Yes.
to look for everything in the upstream is kind of nonsense, because we already know the physics behind it.
Okay. I wish you were my reviewer of my paper. Unfortunately, the reviewers did not accept. And yeah, I'm still going to fight back. Yes, this is the point I really want to make. It is the post-shock conditions. The flow or the boundary layer and the wake will only have memory of what is happening downstream of the bow shock. It doesn't have the memory of the pre-shock conditions. But unfortunately, it's been, rejected. But so that's what our attempt is to, conduct more high fidelity numerical simulations as well as do some experiments to provide more evidence that it is in fact the post-shock conditions that is more meaningful.
Again, this is a little bit nonsense to even do more computation, because it's just the physics of the problem that if they were able to communicate with each other, then a shock wave wouldn't develop.
True. I'm completely, aligned with your reasons and analytical arguments. In fact, we made this in our paper. I mean, I don't want to tell too much things what the reviewer comments were, but the reviewers were asking us to provide experimental evidence, which we don't have yet. We are using the experimental data of Schmidt and Shepard and Avasthi and Thasu and Duveri. We don't have our own experimental data yet, and the reviewers or thought we would see otherwise if we analyze experimental data. So I can probably give more consolidated answer maybe once I have some experimental data myself.
If I may ask a second question too. So in the neck of your wake, you had a frequency of oscillation of 1600, and on the separation point you had a 6400. These are a little.
No, it is 12.7. So are you talking about my preliminary data, simulation data?
True.
Yeah, so it is just this. It's just the doubling. It's just the second harmonic of 6.3.
My question is, are these by any means related to the free stream unsteadiness?
No, in the simulations, we have a very uniform flow as the inlet.
How about aftershock? You don't have any unsteadiness aftershock?
No. In fact, I could play the simulation. The simulation video. We see that the velocity contours are pretty constant. There's no fluctuations in velocity in the free stream, downstream of the bow shock.
Thank you.
There is a question in the chat by Ram Prakash. When you set up the model in the tunnel, will the tunnel edge effects will be a problem in the visualizing?
Yes, I do agree with your point, Ram Prakash. And in fact, very recently, just a week ago, we had a visit from Professor Jewell from Purdue University, and they have access to a quiet wind tunnel because they kind of eliminate the boundary layer to grow within the nozzle before they generate the Mach 4 or Mach 6 condition flow. So we're going to do some experiments in the wind tunnel and also do some experiments in our supersonic tunnel here. Although their Mach numbers are not matched, but we believe we can understand a little bit more about the effect of free stream turbulence and how it affects the wake oscillations.
There is a hand raised by David.
David,
if you unmute.
Hello,
please.
David.
Hi, Krishna. How are you?
Good.
So I have one question about, pretty much this slide. So you said a lot of analysis has been of the quasi-steady problem. These unsteadiness that you're seeing at the low frequencies are very coherent. So
Correct.
Is it possible to use your dimensional analysis to propose a perturbation about the steady solution to analyze? Because if you can do a linear stability analysis about that steady solution, a lot of these questions could be answered fundamentally with a stability analysis.
Yeah, I fully agree with you, David. Yes. I guess the key question would be, with more high fidelity data, either from simulations or experiments, we would also want to know how strong and how far these perturbations remain strong. So yes, you do see a very peak at 6.3 kilohertz, but how diffusive can that be? So that is something we still have to investigate.
Mm-hmm. Okay. Yep. Thank you.
Any
there is a
questions
follow-up question in the chat, I think, from Romfrock about how you're planning to hold it.
Okay, so the mounts. So for the 2D, okay, let me show the 3 cases. For the 2D circular cylinder, we're just going to mount it in the center, and the cylinder will be spanning the full length of the wind tunnel, or at least major portion of the width of the tunnel test section. And same thing holds for the D shape. For the cone, previously, Professor Sudhir Kai, they've used piano wires, very thin wires, hanging off at 4 locations of the cone, and they just apply a lot of tension so that the model can be mounted with very minimal disturbance. And in fact, they even mount it not close to the trailing edge of the cone, rather they used a bit upstream, somewhere around here.
There is another message in the chat, a question. So since you mentioned space vehicles, why did you choose a cylinder as the experimental model rather than an aerofoil?
I mean, and in fact, aerofoil is not going to be working at supersonic or hypersonic speeds. But what we want to eventually build is we want to slowly understand the fundamental origins of these oscillations. So we thought it would be easier, more sensible to use simple geometries and then slowly develop and deal with more complex geometries. And we also believe that these are canonical geometries. There may be a possibility that we can develop lower order models, either like proper orthogonal decomposition modes or SPOD modes that we could use and kind of understand any other complex geometry. Is it possible to kind of construct what the dominant modes will be when you give an arbitrary, a more complex shape object? So that's our hope, or our idea for the future.
Any follow-up questions?
Mm-hmm.
So, maybe I can ask, I'm not from that field, but I was just curious whether the shock will affect, now you have stationary objects, right? They are fixed in space.
Yes.
In reality, when the objects are entering the atmosphere, there will be some motion if they are freely moving. I think this affects, the shock will affect the motion of these objects, or these dynamics will influence the characteristics of the boundary layer behind the objects?
Yeah, that is a very good question, Aman. In fact, Professor Andrew Neely, I don't know if he's still around in the seminar. So we also do some free flight, we call them as free flight tests. We drop these objects and we have a hypersonic flow going past it. And I mean, it may not be, we don't get enough time to fully understand, or for the flow to reach kind of stationary turbulent state, but at least we can see if if the falling motion of the object is going to affect the aerodynamic behavior, like the acceleration, or I'm not a I don't have expertise in aerodynamics, but there are certain parameters one could use to understand the stability of the vehicle. I haven't thought that far, but I wish if we can understand a simple cases, we could then take it and do like a free flight study, and possibly look at if that introduces additional perturbations in the wake.
Okay. All right, then if there are no any further questions, I would like to thank Krishna for willing and agreeing to present, and on the behalf of the AFMS community, thank you for your presentation.
Yeah.
And
Thanks,
this,
Aman. Thanks for the opportunity. I hope I was able to give some insights to into the flow. And
yeah,
I hope you all
interesting.
learned something today in the seminar.
Thank you.
Okay.